Hello, students. So today, next up is the recording of part 2 of the lecture on, optimizing quadratics. So this is the lecture that will wax the most abstract, but contains a very relevant piece of information, and that is the formula that optimizes. Yeah, this is lowercase, cool. So, as we saw in the previous video, optimizing a quadratic is closely related to the idea of finding the vertex. Completing the square. Once you complete the square, you can graph. Once you graph, you have you can optimize by reading the graph. So let's do that. Let's start with the completing the square formula, which you'll remember from last time. Says that if you have a quadratic function, f of x equals ax squared plus bx plus c, and you complete the square to it, you will get the result that f of x equals a times x plus b over 2a squared plus c minus. What does this mean? This means something about the graph. This tells us things about the graph. If you want to graph, well, you should start with y equals x squared. Something that looks like this. You should stretch by a factor of a vertically, and flip over the x-axis if a is less than 0. So what does that mean in terms of the picture? That means either you'll be like still a parabola, but stretched a little bit, or maybe you'll be upside down. So that deals with this symbol and the result of completing the square. Next, think about what these two do. Well, those two just do some shifts, right? You'll go left by b over 2a, and you'll go up by c minus b squared over 4a. So let's think about what that means. So let's deal with this, like this flip over the x-axis only happens if a is less than 0. So let's break into two cases whether or not a is positive or negative. If a happens to be positive, then you don't flip over the x-axis. So you stick with this graph, and then you translate. You translate left by b over 2a. So you have an x coordinate of negative b over 2a. You go up by c minus b squared over 4a. And then you're going to have an upward opening parabola. So you'll see this picture, and then you shift. On the other hand, if a happens to be less than 0, okay, so let's address this bullet point. The resulting graph is a parabola which opens up when a is bigger than 0 and opens, let's color code, down when a is less than 0. So when a is less than 0, we'll see a downward opening parabola, something like this. And so we'll start with that downward opening parabola. We'll go left b over 2a, up by c minus b squared over 4a. So you'll end up at the same point, negative b over 2a, comma, c minus b squared over 4a. And the parabola will open generally downward. And we're interested in optimization, so let's optimize these. So if you want to find the maximum or minimum value from a graph, well, that's easy, right? If you want to find the maximum value of a graph, you want to find the y value that's bigger than any other y value on the graph. For this one, that doesn't exist, right? This is just going to keep going up. So there is no maximum, But there is a minimum. The minimum is right here. And what's the x value that produces the minimum? It's this, negative b over 2a. In the case of a downward opening parabola when a is negative, well, it keeps going down forever. So there's no minimum value, but there is a maximum value, and the maximum value occurs at this point. Well, so let's get these arrows all the way. So the maximum occurs at x equals negative b over 2a. And here is the resulting fact, the vortex formula. The quadratic function f of x equals ax squared plus bx plus c has a vortex at x equal to negative b over 2a when a is bigger than 0. So that's this case. The vortex minimizes when a is less than 0. The vortex maximizes. And that always suggests, like, well, if you know something happens when a is bigger than 0, nothing happens when a is less than 0. What happens when a is equal to 0? When a equals 0, oh, sorry, those two should be in red. All right, cool, sorry. When a is equal to 0, you have the function y equals 0x squared plus bx plus c. This is a line. So if you have a linear function, don't use the quadratic, anything having to do with quadratics. There's something easier, it's linear. All right, nice. So you'll notice some things about this result. You'll notice that I recorded the x value of the vortex, but not the y value of the vortex. We could record the y value of the vortex. In fact, let's do that. The y value of the vortex is y equals this. C minus b squared over 4a. There's a reason I didn't put it in the notes, though, and that's because, let's switch colors. There's no need to internalize this. The whole point of the vortex is that it optimizes. Then you get the y value at the maximum by plugging in. And again, if you don't like remembering formulas in your head, the vortex formula isn't so bad. The vortex is at x equals negative b over 2a. We'll just complete the square. Completing the square, this tells you the vortex formula. The vortex is minus whatever is in that parentheses. Nice. So I think even there are examples on the next page, but let's just do one thing really quick. They're like even real world examples. Let's maximize or minimize. I don't know, negative 2x squared plus 3x minus 5. Let's find the x value that produces the max and the y value at the max or min. So the first thing to note is a equals negative 2 is less than 0. So according to the vortex formula, when a is less than 0, there is a max. This has a maximum value at x equal to vortex negative b over 2a. And let's just write those down. Negative 3 over 2 times negative 2. And let's mess around with what that is. That's double negative becomes a positive. 3 over 4 or 0.75, whichever you prefer. So there's the input that produces the max. The input that maximizes. And let's get the max output. The maximum output is -2 times 3/4 squared plus 3 times 3/4 minus 5. And you know what? That's complicated enough that I'm going to go ahead and resort to using a machine for that. Come now. All right, so I want -2 times 0.75 squared plus 3 multiplied by 0.75 minus 5. That sure looks like -3.875. And right here, I'm using exactly equals because I know that this has a terminating decimal divided by there is like division by 4. In the result of squaring, I'll see a division by 16. That still has a terminating decimal expansion. Nice. All right, cool. So I'll stop this video here. We'll come back in a moment and we'll go through some examples. Let's apply the vortex formula to do some stuff. See you in the next one.